All right, line L3, learning test 2 of L3. Once again, it's the fourth one inside of this section, inside of your binder, just because they're classed together. But it's the one that's going to be talking about describe high impedance ground fault detection systems. Now, we talked about impedance grounding, what it actually is. The impedance is just a large resistance that's designed to go and give us only a tiny amount of fault current. We want to limit the total amount of fault current, which is going to go and limit the total AFI. Most of these are going to be done through resistive grounding devices or reactive grounding devices or zigzag transformers, but there are a couple of other systems that are also available. But no matter what it is, the Canadian Electrical Code will class them all together. You can go into Appendix B to take a look at the note on Rule 10302. It does require that we have got a protection and control, or what we call a P&C system for their operation. Specifically, we have to go and monitor for the following faults, and there's a list inside of your table, or outside of page 38. You have to know if you have got a ground fault on any one of your lines. So if any of these lines goes out to a ground, we need to know about that. We need to know if we would have a ground fault on the neutral that we have over here. We also would need to know if we're going to go and have a ground fault on our impedance, our line that goes between the impedance device and the neutral, or if we would go and lose continuity across here, if this thing would actually go and open up. And if any of those conditions are met, we're going to have an alarm that has to be activated, meeting the following standards. It has to be audible or visual, so noise or lights. It has to be labeled so people know what exactly the issue is, and it must not be able to be silenced or shut off. We don't want people ignoring these because we've lost a critical section on our system over here. Since the impedance ground is going to go and keep our current relatively small, we need to go and make sure that we've got some other way to operate our overcurrent devices. And once again, what we've talked about is the fact that this stuff is going to go and be used for high voltage types of installations. Inside of a high voltage installation, you're going to go and have circuit breakers that are usually going to go and be battery powered. Let's draw in a little battery over here. That battery powered breaker is then going to go and have a little coil that is then going to go and operate the actual trip elements that we are going to go and have over here. And so what we're going to do is we're going to go and monitor everything, and then everything that is monitored is then going to go and send a signal back to our actual overcurrent trip. Most faults are going to go and result in an immediate shutdown. However, there's a couple of times where it doesn't result in it. If you go into your code, it's going to tell you that if this is going to be 5 kV or less, so whatever it is going to be less or equal to 5 kV, we're allowed to go and maintain it, provided that there's only line-to-line loads. We're not doing any sort of a line-to-neutral loads or anything like that. And we're not allowed to have more than 10 amps. That's going to be going through my impedance device, and it has to be rated for continuous use. In those cases, under 5 kV, only line-to-line loads, no line-to-neutral loads, and under 10 amps of total fault current flowing, we're allowed to keep it online, but it has to stay in alarm. Let's talk about the actual monitoring systems that we're going to go and use for these. The monitoring systems over here are showing you just a really simplified setup. Usually this instrumentation is all going to come as part of one unit. You're going to go and take this unit, and it's going to go and have probes that are going to go out to other lines, or in a lot of cases, because we're high voltage, they're not necessarily going to go directly onto the lines, but they might go onto a PT that is going to be monitoring the line instead. Let's go through all of the different connections that we're going to go and have. The first one that we want to go look at is this thing over here, the breaker trip element. Ultimately, we are going to go and control our breaker through this line over here. So whatever we monitor is going to go and send a signal back to that breaker to be able to go and trip it. First thing that we're going to go and look at is going to be our ground connection. That's going to be this line over here. Because we've got a couple of voltmeters here, they need something to reference, so we are going to go and have this reference tied to our ground on the actual ground side itself, where we have the grounding plate. The next thing that we're going to go and take a look at is going to be line voltage connections. These line voltage connections are going to be these three right over here that are designed to go and monitor each of my 3 ungrounded lines. Lines A, B, C are all going to be monitored off of those. They're going to measure the line to ground voltage. Remember, we've got this ground connection, which means that inside of this unit, they're measuring across from there to there with a little voltmeter, well, a big voltmeter inside there. they're going to measure line to ground. They can sometimes be measuring and displaying line-to-line voltages, but this isn't really the purpose of them. They're always just watching that line to ground. Anytime that there would be a fault on an ungrounded line, if one of these ungrounded lines would go and get grounded down, we're going to go and see that line voltage on that line. In this case, if we trace it through this one over here, this line voltage over here is going to go and dip, and so that would indicate that there is going to be a fault on that line. The next thing we're going to take a look at is going to be my impedance voltage probe. And my impedance voltage probe, just go and take this one over here, is going to be a voltmeter section as well that is going to go and run out from my metering section. So it's going across the ground over to the high side, or the neutral side of our neutral grounding device. Under normal condition, we should have no fault current that's going to be flowing through this impedance device that we have over here, which means that we should have 0 volts across it, right? V is equal to I times R, and if my I is going to be a value of 0, we're not going to drop any volts across this device over here. So normally we should see 0 volts that's going to be dropped across it. Anytime that the voltage goes and rises all the way up to a phase value, remember we saw that under faults, this is going to be seen as being at a phase value of voltage. Then we know that we have got a fault as well. And this probe is going to go and not only monitor for our voltage, so we're going to be measuring this thing as a voltage across the ground over here, but in a lot of cases we're also going to be sending a small amount of current. Remember, a voltmeter works by sending current through something. So if I were to take a look at the voltage probe over here, current gets sent through the voltage probe back down to here, completes that circuit. And it is also then going to go and have a little ammeter section inside that is going to be monitoring that current coming back through. It's like what you have seen if for any type of a monitoring system on fire alarm or for security, if you're at all used to those types of systems. We go and put what we call supervisory current. That supervisory current is going to go and flow all the way through here and gives it a very, very tiny voltage rise as a result of it going through there, which this voltmeter is then able to go and read. It's going to go and note that the tiny voltage, so I'm going to go and just call that tiny voltage equals good. It's a good thing for it to have a tiny voltage, and it's monitoring with that ammeter as well to make sure there's continuous voltage through it. And the reason for this is because we are required to know if we lose continuity on our resistance device. If this device would go open, obviously, we would not be able to go and complete this path back through. This ammeter would register 0, and this voltmeter over here would also go and register 0. It's not going to be able to read anything because we cannot drop any voltage across it. Net current is going to be our next section. The net current is going to go and be a window type of transformer that's going to go and encompass all the lines. We know that as long as we've got all the current that is being sent out to the loads is returning back along the same lines, our net magnetic flux is going to be 0, which would mean that this would go and have a value of 0 to it as well. However, as soon as we would go into a ground fault, if this line would go and fault out, we would see that some of that current would go and return, just erase that one there, would go and return through here, which means that it is now outside of this window, which would mean that now our CT is going to register a small amount of current inside there, which is going to go and give us a trip signal as well. Last of all, we're going to go and have our impedance current CT, and this CT is only going to monitor the current that flows to the neutral through the impedance device. Under normal unfaulted operation, there's going to be next to no current. It says no current. It's going to be that tiny small amount of supervisory current that we're going to have going through this device, but that current path follows along from here. It goes like here and then back in for my actual impedance voltage probe over there. This one is going to be upstream of that, which means that it should have 0 amps that's going to be going through. Now, sometimes your neutral is not going to go and stay at neutral. You're going to have imbalances on the systems if one of your lines gets loaded down a little bit. So you could end up with a small amount of current that's going to be on there. But if it senses anything close to fault current outside of a small bit of leakage, then it's going to generate a voltage and it's going to go and cause a trip. This figure shows us fault detection on a resistively grounded system, but we would use the same components if we were dealing with a reactive, so an inductor that we were using for our system, or if we were using zero sequence, a zigzag as a path back through. We could do the exact same thing and just be monitoring the current that goes back up into that zigzag.